Hello everyone. My name is Bastien Sanglard, and I will present to you my work that I currently realizing at the UST at the Université Aix-Marseille. I'm working with Thomas Fasquelle, Séverine Barbosa, and Benjamin Kadoch about the optimization of the secondary reflector for solar cooking for restaurants using a Scheffler concentrator. So first of all, I will present to you the several needs that are required for cooking with for a restaurant. So the first need is the need of high temperature, which induce the use of a parabolic concentrator. The second need is that the cooking hob has to be inside of the restaurant and not outside, which means that the focal point will need to be removed and fixed throughout the year. And the last need is that the cooking hob has to be horizontal. So we'll need a secondary reflector. The only solution that is possible is, as you can see on the picture, a Scheffler type concentrator with a secondary reflector. About the EST objective, they are multiple, and the first one was about the Scheffler concentrator itself, which was defined as the characterization of the performances of and the flux distribution. That was realized by Gabriel Guillet during his PhD. The second objective is about the secondary reflector, which was defined as the optical optimization and characterization of the latter. The third objective is about the cooking hob. Here again, it's about energetical optimization and study of several materials. And finally, the last objective was about the complete installation by realizing the energetical characterization of the cooker, the primary cooker plus the secondary cooker plus the cooking hob. Today, we will focus on the secondary reflector and talk about the optical optimization and characterization of the latter. The method that we used to characterize several secondary reflector is based on the modeling of the system in salt trace. The Scheffler has been modeled thanks to the work of Thomas Fasquelle, who created a script in uh, in salt trace that is open source and is allow us to model the Scheffler reflector. We added to this some constraint. So the constraint about the cooking hob are that it has to be half a meter wide and 0.9 meter long. And the Scheffler has a surface of 8 meter square and a focal length of 1.47 meter. For the secondary reflector specification, they can be deduced from the 3D representation as you can see here. On the top, it's from the outside of the restaurant. On the bottom, it's from the inside. Here you can see that there is two needs. The first one is go through the wall, and the second one is to verticalize the flux to reach the hob. Additionally to those two needs, we add requirements. The first one is that it was necessary to minimize the reflection to lose as less power as possible. And the second one was that the secondary reflector has to be easily made and repairable. This configuration leads us to the first solution, which is the flat reflective tunnel plus an involute. This is the reference case, as you can see here, with the 3D representation on the top, with the tunnel, the involute, which is a quarter of cylinder, and the hob. And on the bottom, you have the salt trace equivalent. This configuration leads to this flux distribution. As you can see, it has been calculated for on the 21st of September with 900 watt per meter square of irradiance. And the result shows a peak flux of 26.3 kilowatt per meter square, a total power of 3,800 watt, and a transmission rate of 85%. The transmission rate here is defined as the ratio between the flux leaving the Scheffler and reaching the hob. So here we have low peak flux, which means that we will have low maximal temperature on the hob. We have a high transmission with 85%. Again, this means that 85% of the flux that is leaving the Scheffler will reach the bottom surface of the hob. And the last observation that we can see, is that the flux is concentrated on the line. In order to increase the peak flux to reach higher temperature, we have decided to see if the use of an approximated compound parabolic concentrator could be useful. After reviewing the literature, we were able to see that for our case, because we have high acceptance angle, CPC with a square entrance and with flat surfaces could be enough. This configuration, again with an involute and with the hub, leads to this flux distribution. Again, we have a line almost at the middle of the hub, but now the peak flux is 45.7 kilowatt per meter square. The total power is 3564 watt, and the transmission rate here it's almost 80%. So what we can see is that we will probably have higher maximal temperature because of the higher peak flux. The transmission, sorry, is a little bit lower, but still acceptable. But the flux still concentrated on the line. And after discussing with the chef, they told us that they would prefer to have a very high spot and not a line to have more gradient in the hub. So to do that, we have decided to change the involute by using parabolic facets instead of flat facets. Here you can see on the figure B that the facets of the involute are not curved, following a parabolic curvature. And this leads to that flux distribution. Here you can see that the peak flux is much higher, of 78.3 kilowatt per meter square. The total power is 3,311 watt, and the transmission rate is 74.2%. We can see that we have a very high peak flux, so probably very high maximal temperature. We have an even lower transmission, but still close to 85%, which is, in our view, acceptable. And now the flux is concentrated on a spot on the center of the hub. So to conclude, we can say that the last configuration was the best configuration, which is composed by an approximated CPC with square entrance and an involute with parabolic facets of 5 centimeters long. This allows a spot at the center of the hub, which allow its large gradient in the hub from in every direction. We have a high flux, so potential high maximal temperature, and the secondary reflector is easily made because it's only composed of flat surfaces or a surface that are curves only in one direction. And it's also repairable because we can imagine a design where all the surfaces can be removed each other, but not necessarily all together. In terms of perspective, the first perspective is the characterization in real condition. So the idea is to build this configuration that I just described, to realize a vertical infrared camera measurement thanks to this setup, and to have real condition observation. First, we were able to have the temperature on the top of the hub and see what it is. And thanks to the work of Gabriel Guillet, we'll be able to reach the flux distribution below the hub. And this will be compared with salt trace result to see if our simulation are good. The second perspective is about the cooking hub characterization itself. The idea is that with salt trace flux distribution and with the finite thermal element method of MATLAB, we can have the evolution of the temperature in time on the top of the hub. Hence, we can try different materials and geometry and see what is the best for our use. This will lead to build one or more hub and test it in real condition with the previously presented setup. Thank you for your attention, and if you have any question, do not hesitate to ask.